This week we are going to do something called matrix vectorization, and we're going to do it essentially by applying the same principles we learned for Gauss elimination and Gauss-Jordan elimination, but with a little bit more context. We're essentially going to apply the same row operations every single time in order to do our factorization. So a little bit of background about this is we need to know what an elementary matrix is. So an elementary matrix is just a matrix that is found by performing exactly one row operation on the identity matrix. So here's identity. For this set of material, we're going to focus on 3x3 systems. Technically, the same principles apply for a 4x4, 5x5, etc. But here's an identity for a 3x3. And there are three different types of row operations. We can replace a row by saying some constant of that row. We can swap two rows. Or we can replace a row by saying that it's a add it to a non-zero multiple of another row. Keep in mind, row operation 3, there is a 1 in front of the row we are adding or replacing. That is very important. So our non-zero multiple is of our additional row, not of the one we are replacing. So I can't say 3R2 plus 3 or plus 2R1. This number needs to be a 1. So there are three different types of row operations, which means there are three different types of elementary matrices. The first type of elementary matrix is an elimination matrix, which is found using our row operation 3, where we replace a row by adding a row to a non-zero multiple of another row. So if I did this to my I matrix, if I said row 2 equals row 2 plus 3 row 1, it would essentially look, I'll do it down here. It would essentially look like this. So 1 doesn't change, 3 doesn't change. Row 2 now becomes 0 plus 3 times 1. 1 plus 3 times 0, and 0 plus 0. So it ends up like this. So I'm going to call it elimination matrix 2, 1, because I replaced row 2 by adding it to row 1. What happens in our elementary matrix is we have this additional term that appears, this additional entry that appears in the ij position. So in row 2, column 1, because I took row 2 and I replaced it by adding it to row 1. This number is called a multiplier. And it essentially tells us how we put our row operation together. It turns out if I took E21 and I multiplied it by some A matrix, then it would do this row operation for me. It would essentially say replace row 2 of matrix A by saying row 2 of matrix A plus 3 times row 1 of matrix A. Okay, so this row operation would appear to have been done inside of my A matrix. Another property of this elimination matrix is that the inverse of this elimination matrix is the same matrix. So it would be 1, 0, 0. 3, 1, 0, 0, 0, 1, but my multiplier changes the sign. So instead of it being positive 3, it would be negative 3. And that's important because it will show up in our LU factorization, essentially, in our factorization of matrices. That's an elimination matrix. I'm going to skip over a bunch of the notes and go down and talk about a permutation matrix. So a permutation matrix is an elementary matrix where we are swapping rows. So we're doing row swaps, row operation 1. Or we're swapping rows. So if identity looks like this, permutation 1, 2 would look like this, where I swapped rows 1 and row 2. So same rows, just in different order. That's a permutation matrix. So we have elementary matrices. An elimination matrix is where we apply row operation 3, where we do our elimination step on identity. A permutation matrix is where we swap our rows. And it turns out that the inverse of this matrix is the same thing. Once again, that comes into play when we put together our matrix factorizations. And it turns out if I do P times A, it essentially does those same operations as if I swapped the same rows. So rows 2 and 1 inside of my A matrix. So that is my introduction to elementary matrices. We will see them show up, and you should know how to construct them.